Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shirdevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist of Basic Electrical Engineering and Class 12th Physics in our chapter Alternating Current Circuits, we will understand the behavior of pure inductor in alternating current supply and will learn a coil configuration has a property of inductance which in a time varying sinusoidal alternating current demand a sinusoidal alternating voltage of the same frequency, but current and voltage got a 90-degree phase difference with current lags voltage, and in this process when current rises inductor stores energy, and when current decreases inductor release the same stored energy of magnetic field, and average power consumption by such circuit in alternating supply is zero, and such power is known as reactive power. So let's understand all about pure inductance behavior in alternating current supply. Inductor is a two-terminal passive component. This is a coil configuration in which when current flow through these turns, they produce a magnetic field, and this inductor configuration can store energy in that magnetic field. The property of inductor is known as inductance, and inductance is felt only when current is time varying. In DC current condition, inductance become ineffective, but in time varying current conditions, this coil configuration or inductance oppose changes of current taking place in it. In our practice, inductor is also called as choke, reactor, or just a coil. Inductor is formed from several turns of thick, high conductive conductor wire, and often these turns are wound around a high permeable ferromagnetic core, and for higher frequency operation we use ferrite core, and for normal power frequencies we may use silicon steel, and high permeability of core will increase the inductance property of this coil configuration. Flow of current in coil turns produce a magnetic field around it, and field flux produced by current carrying coil is directly proportional to current flowing through the coil. And if this current is time varying, then time varying current will produce time varying flux linkages with coil turns, and as per time rate change of flux linkages, there will be induced EMF in this coil configuration, and as per Lenz's law, this induced EMF produced by time varying current or time varying flux linkages oppose the very cause the variation of current in coil. So this coil configuration got a property to oppose changes of current in itself, and whenever there is a change of current in this configuration, there will be an induced EMF directly proportional to rate of change of current with respect to time, and this induced EMF tries to oppose the changes of current taking place in it, and this opposition to change of current is known as inductance. When time varying current produce time varying flux linkages, as per Faraday's law of electromagnetic induction, as per time rate of change in flux linkages, there will be induced EMF, and this induced EMF is directly proportional to rate of change of current with respect to time, as flux is proportional to current and d phi by dt is proportional to di by dt. And as per Lenz's law, this induced EMF try to oppose the changes of current, and to maintain such changes of current in this inductor circuit, we have to apply an external source voltage to counter this induced EMF, and external applied voltage is equal to induced EMF, and we can say to maintain time rate of change in current, we have to apply a voltage which is proportional to rate of change of current with respect to time, and this proportional relation can be converted into equality, and for that we use a constant denoted by this capital L letter, and this L constant is known as coefficient of self-inductance, and it is measured in Henry unit. Flow of current in a coil configuration produce magnetic field around it, and if this current is time varying, and to maintain time rate of change of current, we have to apply a voltage which maintain di by dt in this coil configuration, and with that voltage, if dq small amount of charge is flowing, then elemental work done is given as E dq, where dq is I dt, and in place of E we can write L di by dt, and integration of elemental work become total work done, and total work done is integration of Li with respect to I, and to raise current from 0 to capital I, the total amount of work done will become half Li square in joule, and this much amount of work get stored in inductor with the magnetic field produced by this current, and when this current increases, the stored energy in inductor increases as shown here by this half Li square relation, and when the magnitude of current decreases, the strength of magnetic field also decreases, and stored energy of inductor get released to external circuit components, and whatsoever the direction of current in alternating circuit, stored energy is a square function of current, so energy is always remain stored even when the direction of current or the direction of magnetic field is changed whenever there is a current in coil. Consider an inductor of L Henry connected in series to a standard reference alternating current given as I equal to Im sin omega t, whose t0 instantaneous magnitude is 0 and it is increasing in a non-linear sinusoidal manner in positive direction. Here in this expression I equal to Im sin omega t, this Im is amplitude or peak magnitude of sinusoidal alternating current, and this omega is angular frequency of alternating source. Now this time varying alternating current produce time varying alternating flux linkages with coil turns, and as per rate of change of flux linkages there will be induced EMF that oppose the changes of current taking place. And to maintain this time variation of current in this L Henry inductor, we have to apply a voltage proportional to rate of change of current with respect to time, and proportionality constant is coefficient of self inductance of this coil configuration, and VL is equal to L di by dt. So in this inductor of L Henry, the applied voltage across inductor is directly proportional to time rate of change of current, and VL is L di by dt, and in place of this time varying alternating current we can write standard reference sinusoidal alternating current expression I equal to Im sin omega t, and when this is differentiated, Im being constant come out of differentiation, and differentiation of sin omega t is omega cos omega t. Now this product of Im and omega L in front of this cosine function become amplitude of voltage that is required to produce time variation of current, and this amplitude is Vm equal to Im omega L, and we can write cos omega t as a sine function with 90-degree leading phase, and we can say when current is Im sin omega t, the voltage across inductor is Vm sin omega t plus 90, where peak magnitude of voltage across inductor is equal to peak magnitude of current through inductor multiplied by omega L, and here the voltage across inductor leads current through inductor by 90-degree, or we can say current in inductor lags voltage in phase by 90-degree. The similar type of current voltage relation in an inductor can be obtained by considering voltage across inductor as standard reference voltage VL is equal to Vm sin omega t, which with phase angle 0 have T0 instantaneous magnitude 0, and when this voltage is applied as per instantaneous magnitude of voltage, there is instantaneous rate of change of current with respect to time, and applied voltage and di by dt are proportional to each other, and proportionality constant is coefficient of self inductance of this coil configuration, and this differential equation can be separated in terms of current as di equal to 1 by L VL dt, and by integration we can say current flowing through an inductor is 1 by L times integration of voltage across inductor with respect to time. And in this integration equation, if in place of voltage across inductor we substitute standard reference sinusoidal alternating voltage Vm sin omega t, where Vm is peak magnitude of supply voltage and omega is frequency of alternating sinusoidal voltage, then this Vm being constant come out of integration, and integration of sin omega t becomes minus cos omega t over omega, and minus cos omega t can be written as sin omega t minus 90 degree, and this prefix to this sine function is Vm upon omega L, become amplitude of sinusoidal alternating current flowing through inductor, and this Vm upon omega L is Im, and current through inductor become Im sin omega t minus 90 degree, where Im, amplitude of current flowing through inductor, is given as amplitude of voltage divided by omega L, and this current lags voltage by 90 degree as we have derived earlier. In an inductor, voltage across inductor is directly proportional to time rate of change of current through it, and when continuous time varying sinusoidal alternating current passes through an inductor, there exists a sinusoidal voltage across inductor of the same frequency but leads current by 90 degree, and here the peak magnitude of voltage Vm given as peak magnitude of current multiplied by omega L, and this product of angular frequency and coefficient of self inductance is known as XL or inductive reactance. And in terms of RMS value, if we divide both sides by root 2, then amplitude of voltage divided by root 2 become RMS voltage across inductor, and peak current divided by root 2 become RMS current through inductor, and this relation is just like V is equal to IR relation, and it says that this XL known as inductive reactance is that property of inductor which oppose flow of alternating current and demand proportional voltage to flow of current, and in an inductor alternating current and voltage across it are proportional to each other. Here this inductive reactance is product of angular frequency and coefficient of self inductance, or is equal to 2 pi FL, and this inductive reactance expression clearly indicate that inductive reactance is directly proportional to frequency, and there exists a linear straight line relationship between inductive reactance and frequency of alternating current passing through inductor. Inductive reactance of a coil of coefficient of self inductance L Henry is omega L or 2 pi FL is directly proportional to supply frequency, and with a source of constant voltage and variable frequency, if we increase frequency of source, the inductive reactance directly proportional to frequency increase linearly, and current through the coil voltage divided by inductive reactance with increase of frequency. When inductive reactance increases, current inverse proportional to frequency decreases in an hyperbolic manner, and for a very high frequency condition, inductive reactance become very high and current get limited by such inductor placed in high frequency alternating current supply. And for DC supply, frequency is 0 and inductive reactance as per this relation of 2 pi FL for DC frequency 0 become 0, and we say inductor behave like a short circuit in DC supply, and in DC supply current is controlled by only the resistance of circuit, and inductor become ineffective in DC steady state current conditions. In an inductor, the sinusoidal alternating current flow Im sin omega t result as cosinusoidal alternating Vm cos omega t or Vm sin omega t plus 90, and both sinusoidal alterations of current and voltage are of same frequency, but the two got a phase difference of 90 degree, and from positive peak of instantaneous voltage, the positive peak condition of instantaneous current occur after a phase difference of 90 degree, or we can say current lags voltage by 90 degree or 1/4 of a cycle, and we can remember the phase difference of 90 degree between voltage and current in an inductor as opposite to capacitor. In capacitor, current leads voltage by 90 degree, and in inductor it is just opposite, and current as shown by orange wave shape lags voltage shown by cyan wave shape by 90 degree in phase. When current through inductor is a sinusoidal wave and voltage across inductor is a cosinusoidal wave, then identical phase conditions, say positive peak of voltage will occur 90 degree ahead of current, or similar phase conditions if we see of voltage and current, then current lags voltage by 90 degree, and when sine and cosine alteration got a 90 degree phase difference or a quarter cycle phase difference, when one out of voltage or current is at peak value, the other one is at zero value, or when one is increasing in one direction, other one is decreasing in its previous direction, and vice versa. As it is clear from this wave shape, when current got zero instantaneous value, voltage is at either positive peak or negative peak, or similarly, when current is at positive peak or negative peak, voltage is having instantaneous value 0. The relation of current through inductor and voltage across inductor is VL is equal to L di by dt, and when VL is positive, all through positive magnitude of instantaneous voltage, di by dt is positive, so current is either increasing in positive direction or decreasing in negative direction and increasing in positive direction, di by dt is positive. Similarly, for all instantaneous value of voltage negative, di by dt become negative, and continuously current decreases from positive peak to negative peak during negative half cycle of voltage across inductor. And when voltage got a higher instantaneous magnitude, when current is crossing 0, voltage got peak positive magnitude, di by dt is more, so current is changing at a faster higher rate. And when instantaneous value of voltage becomes 0, VL becomes 0, di by dt also becomes 0, and current, which is increasing at a higher rate initially when voltage is high, decrease its rate of increase with decrease of instantaneous voltage, and di by dt become 0 at positive peak when instantaneous voltage become 0, and after that when voltage across inductor become negative, di by dt become negative, and current, in place of increasing earlier, start decreasing afterwards. The graphical representation of the phase relationship between sinusoidal alternating variation of current and voltage in an inductor can also be represented by phasor diagram. Here current through the inductor is a standard reference alternating current wave with phase angle 0. So its current phasor is denoted on horizontal line with 0 angle from horizontal reference, and voltage is a cosine wave or leads current by 90 degree, and that leading position of voltage is denoted by voltage phasor position 90 degree anti-clockwise from current phasor as shown here. And the projection of current phasor and voltage phasor on vertical axis represent T0 instantaneous magnitude. Current got 0 instantaneous value as projection on vertical axis is 0, and voltage got the full peak magnitude as instantaneous value. Both current through the inductor and voltage across inductor are rotating vector or phasor, and they rotate in anti-clockwise direction with velocity equivalent to angular frequency of supply, and as they rotate, their projection on vertical axis in first quarter represent that instantaneous magnitude of voltage is decreasing and instantaneous magnitude of current is increasing, and when voltage become 0 in instantaneous magnitude, current will attain its positive peak as projection on vertical axis. And in next quarter, when phasor rotate, the projection of voltage phasor on vertical axis represent negative instantaneous magnitude, and projection of current phasor on vertical axis represent reduction in instantaneous magnitude of current. And after half cycle, voltage become negative peak and current become 0, and further rotation of phasor represent instantaneous magnitude variation of current and voltage, and one rotation will represent one cyclic variation. The product of instantaneous voltage across inductor and instantaneous current through inductor gives instantaneous power of inductive circuit, and when current is standard reference sinusoidal Im sin omega t form, the voltage is Vm cos omega t, leads current by 90 degree in phase, and the instantaneous power become Vm Im cos omega t sin omega t. And if we use sin 2 omega t identity, which is 2 sin omega t cos omega t, then product of sin omega t cos omega t become sin 2 omega t by 2, and Vm by root 2 is Vrms and Im by root 2 is Irms. So Vm Im by 2 become Vrms Irms product, and we can say instantaneous power is a double frequency sinusoidal variation with peak magnitude or amplitude, product of RMS voltage and RMS current. And we know for any sinusoidal or cosinusoidal wave, the full cycle average value is 0. So the average power in an inductive circuit where current lags voltage by 90 degree in phase is 0. In a pure inductive circuit, sinusoidal alternating current shown by orange wave lags sinusoidal alternating voltage by 90 degree phase difference. Here voltage is in cyan wave shape and current is in orange wave shape, and the instantaneous power product of instantaneous voltage and instantaneous current is shown by black wave, which is a double frequency sine wave. When current completes one cycle, this power completes two such cycles. In first quarter of current, when current is increasing, the product of positive voltage and positive current is positive and power is positive. And in third quarter, when current is increasing in reverse direction, voltage negative and current negative, product is positive power and power is positive. In both these quarters, increasing current in any one direction increase the magnetic field produced by current carrying coil, and energy stored in that magnetic field increases, and that increase of energy comes from positive power of the source, and source supply electrical energy to inductor circuit, and inductor stores that energy in magnetic field. And in other two quarters, when current is decreasing in any direction, one out of current and voltage is positive and another one is negative, and instantaneous power in those two quarter is negative. And in those case, when current is decreasing, the magnetic field associated with that current, whether current is in one direction or other direction, the direction of magnetic field may change, but the magnitude of magnetic field is decreasing in both case, and this decrease of magnetic field release energy stored in magnetic field, and that release of energy from inductor represent negative power for alternating source, and power is negative in one complete cycle. During increase of current with positive power, inductor stores energy, and during decrease of that current in a symmetrical manner, the same amount of energy is released by inductor from magnetic field, and power got a negative half cycle just like previous positive half cycle, and total energy consumption by inductor by this way becomes 0. In sinusoidal alternating voltage supply, when current lags voltage by 90 degree, the instantaneous power is a double frequency sinusoidal curve as shown by this black wave, and in these conditions, though voltage got effective RMS magnitude, current also got effective RMS current, but the average power in inductor circuit is 0. And we say when current and voltage got a 90 degree phase difference, the power flow associated in such circuit is only reactive power, and such reactive power is only stored and released in equal amount and not consumed. So inductor during increase of current stores energy with positive power from source, and during decrease of current release the same amount of energy with negative power of the source. In an inductor, time varying sinusoidal alternating current flow demand a proportional time varying sinusoidal voltage, but the two got 90 degree phase difference, and average power consumption for such current flow in inductor from external voltage source is 0. So we say in such pure inductive circuit, when current and voltage got 90 degree phase difference, the power associated with voltage and current is only reactive power, which get stored and released only and not consumed. The RMS voltage across inductor and RMS current flowing through inductor got a product known as reactive power only, denoted by capital Q and measured in volt ampere reactive unit. And if in place of VL we write current multiplied by inductive reactance, then reactive power can also be expressed as IL square XL, and this reactive power represent only store of energy in magnetic field in an inductor when current is increasing, and release of same energy will take place when current in inductor is decreasing. So it is only store and release, and there is no average power or real power in inductor when current lags voltage by exactly 90 degree. For a given supply frequency, if coefficient of self-inductance of inductor is higher, then it would have higher amount of inductive reactance, and for same rated voltage with higher inductive reactance, the magnitude of current will decrease as higher amount of self-inductance generate or require higher amount of voltage for same amount of di by dt. Similarly, if we increase supply frequency for same amount of self inductance, inductive reactance will increase, and increase of inductive reactance will either reduce current flow magnitude for the same supply voltage, or for maintenance of same current it will require higher amount of supply voltage. So when frequency or coefficient of self inductance increases, it will increase inductive reactance, and from constant magnitude of voltage we'll find amount of current flow will decrease. We hope this beautiful learning video has explained each and every learning aspect of pure inductance behavior in alternating current supply. Now with VL is equal to L di by dt relation, you could understand that in pure inductance, current lags voltage by 90 degree, and in those conditions, average power in inductor is 0, but there exists reactive power, and inductor store energy when current increases and release the same stored energy when current decreases. Our other learning video of the same playlist are equally useful to enhance your subject understanding and exam score. If you need online doubt clearing classes or exam centric dedicated notes from our channel, do join our YouTube membership. Happy learning. Have a nice time. Thank you very much.